Very good morning, and today basically I will start the iron blast furnace. After the introduction, today's first lecture will be on the iron blast furnace. The concept that will be covered, actually the shape of the blast furnace, how does the blast furnace look like and why the shape is like that, and then we will talk about the various zones in the blast furnace on longitudinal cross section and various reaction in the blast furnace. Okay, so this is a very nice picture and taken from the book of A.K. Vishwas. This is the blast furnace on a longitudinal cross section look like. Now different section, let us start with the different section, and at the top we can find there is a charging device. Okay, that is the top. This section is coming, yeah, this section is the charging device, and that is the top cone, and here we have the charging device where there are it is shown the bell charging, and then most recent charging system is the bell-less charging, and but it is situated on the top cone. And then we can find the next region is called the throat, a cylindrical portion that you can find here. So this is called the throat, and in throat is basically used for the final burden distribution devices are there. This is the final distribution, like in case of bell-less charging there is a handle or the chute that basically distributes the material, and also in case of the bell charging there are some armor is there. Basically it is shown that is the armor, basically it is a movable throat armor that basically deflect the material at different cross section of the blast furnace. Okay. So although there was some limitation with the bell charging in distributing the burden, with bell-less charging we can exactly keep the material where we want across the cross section. So this is the throat, and after throat we have the shaft. This is a very important region in the blast furnace, that is called the shaft. That is from here to here, this portion, this total portion is called the shaft, and here basically most of the reduction take place. There is the gas solid interaction and the burden get reduced mostly in the shaft region, in the solid state, and it is very important portion in a blast furnace because here you have to maintain a proper permeability of the bed so that gas solid interact significantly. I will come to later on. And also you can find that the stack is little tapered out. It is not perfectly cylindrical, it is basically cone. So it is tapered out like this. So this tapered out is basically to accommodate the expansion of the solid, because here the cold solid is coming down and the hot gas moves up, and it is a very counter current gas solid reactor, and there is an exchange of heat. As a result, solid get preheated in this zone. As the solid comes down, it gets preheated, and obviously it will expand in volume. So to accommodate that volume, you should have this type of tapering on the shaft. Another thing you can find on the shaft wall, there is a cooling arrangement is there, because the heat from the gas, it will go to the solid, as well as some amount of heat, significant amount of heat will also cross the refractory break, because there is a temperature gradient also, because ambient is 30 degree and inside is say 800-900 degrees centigrade. So there is a huge gradient. So heat will also flow in this direction. Heat will internally flow. Heat will be exchanged between solid and gas inside the furnace, as well as a significant amount of heat can cross this way. And as a result, the refractory will be heated up, and since the refractory do not have much of is very insulated type of thing, it does not allow the heat to go through, so it will accumulate heat and it will be heated up. That is, the refractory gets heated up very soon, because lot of heat flux come, but it does not allow that heat flux to go into the system, because refractory is usually then insulating. As a result, what happens, the refractory get heated up soon, and unless you cool the refractory, the life of the refractory will be less. So it is very important to cool the refractory such that you can increase the lining life, because blast furnace runs for long time, and after that, because once you disrupt the blast furnace process, then it takes a lot of time again to start it. So basically blast furnace is a steady state process and continues for a long time, and then you have to look after this refractory, such that the refractory doesn't worn out very quickly, such that again you have to stop the blast furnace and repair the refractory. So that is meaningless. So as a result, you have this type of cooling arrangement is also there. So where basically you can cool the refractory lining, and it is done basically using what is called the copper cooled refractory. That is the copper cooled, that is the copper cooling, copper plate, that is the copper cooling pellets. Also called the stibs, S-T-A-B-E-S, copper steps. So this is called the copper steps. The copper cooling plates are there. This is called the stibs, and you can use that to cool the refractory. Okay. So this is about the shaft. So shaft you understand, and after the shaft, basically stack cooling pellet, basically this is the copper cooling pellets on the stack. Basically here in the plates you have arrangement for cold water going and hot water coming out, and since the copper has a high conductivity, it extracts the heat very fast and deliver it to the liquid, and liquid takes the heat away. Okay. Now after the shaft we have the boss region, that is the belly region. There is another cylindrical portion you can find. This is another cylindrical portion, right, and this is called the belly. This is called the belly. This cylindrical portion is called the belly, and here basically the softening starts. There is the solid softening starts here. The solid means basically the iron and slag softening take place, because coke doesn't soften, right. So it is the two material, that is the iron as well as the slag softening taking place in this here. And just below the belly you have another region that is called the boss. So this is the boss region. This region is called the boss, you can find, and there is a tapered in. This type it is tapering in. Again, why it is tapered in? Basically here the solid become liquid and it shrink in volume. Okay. So since it shrinks in volume, you have to tapered in. So some tapering is required such that you can reduce the volume inside the blast furnace again. Otherwise, it will create voids and charge from the top can slip into the bottom suddenly. Okay. So you have to do not allow to create any void inside the blast furnace. Since the liquid shrink, so you accommodate for the decrease in the volume. So this portion basically you have some decrease in the volume, and that is called the boss. And just below the boss you can have this is what is called the hearth. Below the boss you have the hearth. This is basically the reservoir for the, here in this region you have the reservoir for liquid metal and the slag, and you can take out the slag through the slag notch, because the slag is basically very lighter. So when the slag metal forms in the lower part, slag floats off and the iron remains in the lower part because it is heavier, and you can take out the slag from the slag notch here at the top, and you have an iron notch just at the bottom here. Here you have the iron notch. This region is the iron notch through which you can take out the hot metal, and this is the slag notch through which you can take out the slag. Okay, so these are the different section, and below that it has the foundation. So these are the different section in the blast furnace that you have understood. And now let us see the zones in a blast furnace. What are the different zones that is in the blast furnace? First zone is the dry zone. This region, top region, if you just say the blast furnace, you can divide into the initially, that is two parts. One is the dry part, and another is the lower part is the wet zone. So one you have the dry zone where the solid remained, that is the burden remains solid, and wet zone where the burden becomes liquid. In the lower part basically the liquid, gas moves up. In the liquid zone gas moves up against the liquid, and in the dry zone the gas moves up against the solid. So, here basically the gas solid reaction, here in this case there is the liquid gas interaction is there in the wet zone, and that is also very important. In the wet zone and the gas zone, in both the region you should have sufficient permeability such the gas can pass through. Okay. And these are the zone, and another zone that is the most important zone that we can find, that is the combustion zone is there. Combustion zone is at the 12 location where the gas is entering, right. Here the gas is entering through here in this portion, that is the air blast is coming through here, and then this is called the raceway. This is the region where basically the gas burning take place. Okay. So, that is called the combustion zone. What are the reaction you can expect? First carbon is coming and is form the CO2, and then CO2 again form the CO, because CO2 is not stable, it reacts with the carbon forming the CO gas. So, basically what happens, that is the carbon burns in this region and forms CO. This is the region carbon burns in presence of the air, it burns and form the CO and that moves up. That is basically the combustion zone. I will come to it little bit. Here you can find, this is the combustion zone. You can see this way, you can better to see it, because this is the two air you can find on the longitudinal cross section, only two air you can find. Actually there are number of two airs in the plan view that you can find, and this is all the raceway. This is basically these are the raceway, these are whatever you can find, these are all raceways. So, you can find this is the raceway where the carbon burning take place in this region only, not beyond that point. Beyond that point oxygen does not reach. So, this region you can find the center region, this is the region where basically some of the cokes are there which remains inactive, that does not take part into the reaction, because oxygen does not reach at the core of the center of the Boss region, in the center of the Boss, where basically the oxygen cannot reach, because oxygen raceway is the region where basically carbon oxygen reaction taking place and oxygen does not penetrate inside. So, there the carbon remains inactive. In the longitudinal cross section you can find the same zone. This is the inactive carbon zone, you can find like this. This is the inactive carbon zone in the longitudinal cross section. So, this region is basically called the coke remain inactive, and it is called the dead man's zone. Okay. This is the dead man zone where basically the carbon do not participate in any kind of reactions. Okay. And in a steady state furnace, basically blast furnace is a steady state process. You have input, you have output for long time, whatever the amount of input you are giving, same amount of output you are taking it out. Okay. So, it is after the blast furnace starts, after it starts for few hours, it becomes a steady state. Initial when you start the blast furnace, after few days it becomes in steady state, and basically we are showing you a steady state blast furnace. So, in the steady state blast furnace you have this type of dead man's coke. So, this is a very important zone, because this is the coke that is the solid, and it basically holds the overburden, all the overburden. Otherwise everything in other region, all the solid is molten, and even whatever the coke that is coming down in this region, they basically burn in the raceway. Okay, all the cokes also burn away. So, whatever the coke comes here and then burn away. So, burns. So, only the coke in this region that remains unreacted and solid, and that basically holds, it helps in holds the overburden. And this dead man basically it floats over the hearth, liquid hearth, okay, over the buoyancy. It can float, it can be floating dead man or it can be sitting dead man, depending on the situation. That is the what is the buoyancy you have, depending on that it can float or it can sit. So, either it can be sitting dead man or a floating dead man, right. So, that is why another zone, that is the dead man's zone, as I said. So, 4 zones we have discussed, right. And this is actually in the combustion zone, there is 2 area you can find A and A prime. Basically here in this region, basically here in this region, there 2 regions are there in the combustion zone. In the red region, first is the A, in the A region, basically the reaction that take place, because when air comes, it directly reacts with the oxygen, right, forming the CO2. and then when the CO2 cross this envelope, comes to the next envelope, then this CO2 is not stable. In presence of carbon, then it forms the CO gas. It forms the CO gas, right? In presence of carbon, it forms the CO gas. So the overall reaction is basically C plus half O2 forming CO. This is the overall reaction of the combustion zone. Actually, first when the air comes, because of high partial pressure of oxygen, it reacts with the carbon forming CO2, but CO2 is not stable. When the CO2 come out of this zone here in A prime zone, then CO2 react with the carbon forming the CO gas, right. So overall reaction, this is the overall reaction of combustion zone, overall reaction in combustion zone, right. So that way I wanted to say. Now another very important zone is called the cohesive zone in the blast furnace. Basically I talked about the softening, and where does the softening take place? Is it at a particular horizontal line, this is solid and beyond that everything liquid? No, it is not like this in the blast furnace. In the blast furnace, where the softening of the solid take place, that is called the cohesive zone. It is very interesting. If you see, this is your this zone, you can find this is the coke, this is the purple color, it is shown as the coke, and in this next this color, little yellowish color, this color is shows the your ore. So this is coke and this is ore, again this is coke, this is ore, this is coke and ore, like this. Now you can find that the ore layer, when it is coming and near the center in this region, it has become red. Red means it has softened. So, okay, so ore was here solid, in this region it gets softened and it become red. And then you can find the coke. Nothing happens to the coke because coke doesn't soften at that temperature. So this coke layer remain constant. And then again ore layer, if you see, it comes here and then it soften and again it becomes red here, right. So again coke layer, alternate layer is the coke. Basically when the burden is charged in the blast furnace, you charge the ore and coke, limestone, ore, coke, limestone, like that. So they remain more or less in a layer wise fashion. Although there is some intermixing at the interface, you cannot have a sharp interface like this. There is a diffuse interface, but you have obviously an alternate layer of ore and coke. So ore and coke, what happens? You can find that coke doesn't remains unaffected. As it moves in this direction, the temperature increases because center region is temperature is more, and the periphery region temperature remains little less, because most of the gases, because the gases find a easy path through the center region, this becomes porous, and periphery region, in the periphery you have the solid is because of resistance, solid movement is also restricted and all the fines are accumulated is also there, okay, fines because of abrasion and all these things, fines generation and all these things are there, and this type of profile is formed. First of all, if you want to understand this, let us understand why the stroke profile is like this little bit, because stroke profile is like, because towards the center, if you see, the resistance to flow is less compared to the resistance to flow across the periphery because of friction. Because of friction, the ore or the charge won't be able to come down as fast as it could across the center region. So center region charge will move faster compared to the periphery. As a result, what will happen? The stroke line will be like this. It is called a V type of stroke line, V stroke line, right? V type. So this is, or there is M type stroke line also, which is very important, later on you can come to know. But usually this is a V type of stroke line you can find, and the ore also you can find this way. This way it is aligned. The burden is aligned in the V way. It is not horizontal as you can find. It is aligned inclined. Second thing is that, so whatever we are finding, that after coming a certain distance, as the ore comes down near the center, it start softening. So here it has start softening here, and you can find the coke remain unaffected. So what happens? When the gas pass through it, it cannot pass through this coke region. Gas cannot pass through this red region. Red region means the softened iron ore or the slag. So it will not. So only it can pass through this coke region, okay, which is called the coke slit. right. So, it has come. So, descending old layers separated by permeable layers of coke undergoing softening metal. So, you can find this is called the cohesive zone. That is, this is the red region, the softened iron and the slag, and this is the coke slit through which the gas can pass, and then this region is the your softened iron ore and then coke. So, this region, this is called the cohesive region, where basically the softening take place. Now, why the shape is like this, as I said, the temperature of the gas will be here little higher. So, obviously, the solid temperature also will be higher, and periphery the temperature will be lower. So, if you see the isotherm, this is basically the isotherm, this is the softening isotherm, this is one start of softening, this is the end of softening, right. So, basically these are basically the two isotherm, and isotherm obviously it will look like this. So, these isotherm, when the ore crosses this isotherm, it become red, right. Similarly, when it is coming, it crosses the isotherm, it become red, and it crosses the isotherm, it become red like this. So, the ore softening take place in this region between these two isotherms, the start of softening and end of softening of the iron as well as the slag. Okay. Slag is also there. So, these are basically your softening, and the coke remains there which acts as a passage of the gas. Coke only allow the passage of the gas, and this is called the coke slit. So, there is alternate softened in the cohesive zone, alternate fused mass of iron and slag, and then you have a coke slit, and again fused mass, and then coke slit, fused mass, coke slit, and in this fashion. So, this is there through which the gas passes. Another interesting thing you can find, that is the gas, when it is generated in the raceway, it can pass through the central region also through this coke slit, and the gas can pass through the periphery also through this coke slit. So, there are coke slit near periphery, these are the coke slit near the center. So, this different coke slit allow the gas to pass throughout the cross section. Of course, the majority of the gas pass through to the center. Majority, and I will say most of the significant amount of gas, more amount of gas pass through the center region than to the periphery region. Because as we will see later on also, for this type of stock profile, the periphery is also permeability is little less, because periphery because in the periphery we will come to that thing. Basically, if the fines are charged, they try to stick to the wall because of resistance. There is a lot of frictional thing, the charge cannot move away. So, because of less permeability, but you can see that the gas, when it is coming up, it finds the path both through the central region as well as periphery region across this. It allows to pass through. If there is no, since there is alternate coke slits, it allows the gas to pass through both the periphery as well as the central region. Maybe in the central region little more gas pass through because of permeability is higher. Usually in the central region permeability is higher, that allows the more gas to pass through compared to the periphery. That will come later on when burden distribution, all these things we will discuss. But the coke slit basically allows your path. Now come, that is the temperature profile and reaction in the blast furnace. This is a very interesting point, that is this is the temperature profile of the blast furnace gas. Dotted line is the gas and solid line is for your solid line for the solid, and this is for the dotted line is for the gas. And this is the distance above the tuer. Suppose here you have the tuer, your tuer is here, that is your tuer is located here, and distance above the tuer. So, what you can find, that is the gas temperature, because the gas from the combustion zone, it has a very high temperature, more than 200, more than 2000 degrees centigrade. So, the gas then moves up and it transfers the heat to the solid, and the solid also this is the Kelvin basically, that is why the temperature in Kelvin 2200 Kelvin or 1200 Kelvin means around 1000 degrees centigrade, right. So, around 900 to 1000 degrees centigrade. So, here basically in this region you can find, here there is the solid from 1900 degrees centigrade, it comes to around your 1300 degrees centigrade solid, and the gas loses its temperature from 2000 to say around 1900 degrees centigrade in this region. So, in this region, this is the lower part of the furnace, the complete heat exchange take place, and then you can find in this region the temperature between the solid and gas, there is no difference, in the temperature difference is not there. So, this is called the isothermal zone, because there is no heat exchange between the gas and solid in a significant portion of the furnace, and it is also called the thermal reserve zone. 1200 K. 1200 K means around 923 degrees centigrade roughly. So, 900 degrees centigrade. So, this region is called the isothermal zone, and then again you can find beyond that region, above this region, because the solid is coming at 30 degree and then it is heated up to 900 degrees centigrade and heat exchange take place from gas to the solid. So, basically you have a central region, a significant portion of the central region, that is called the thermal reserve zone or the isothermal zone, right. Thermal reserve zone, you can find this is called the thermal reserve zone, thermal reserve zone. And in the above also there is a zone, in this region also it is called the chemical reserve zone in the top here in this region. So, it is the thermal reserve, that is the thermal So, this is called the thermal reserve zone, okay, thermal reserve zone. And above this there is also a some, that is the FeFeO reaction come to equilibrium, will come to later on. So, this is the thermal reserve zone. Or now what are the reaction that you can find in this region is that, sorry. So, what are the reaction you can find in the top part of the furnace, what reaction that take place? I will come to this this temperature distribution later on also, but you can find that there is a exchange, there is a central region where basically there is no heat exchange of gas, called the thermal reserve zone. Now, the reaction in the upper region, that is the reduction of higher oxide, basically take place in this region. And as so basically here the reduction of higher oxide that take place, and then we have, these are the two reaction basically take place, basically Fe2O3, that is the iron oxide plus CO forming that Fe3O4 and CO2, okay. So, this reaction take place because as we will see that we have seen it, that is Fe2O3, we have talked about that, yes. Fe2O3 has a very high potential, because among these various oxide that present in the Ellingham diagram, we have seen that is the Fe2O3 position is much higher in the Ellingham diagram, and so it has a very high oxygen potential. So, it can be easily reduced to Fe3O4, and then Fe3O4 will be reduced to FeO, and then finally Fe will be reduced to Fe. So, we will come to that thing. Basically higher oxide, you can see these three forms, that is the, if you start with the hematite, hematite first Fe2O3 will first reduce to magnetite Fe3O4, because it has a very high oxygen potential compared to Fe3O4. So, it will first reduce to Fe3O4, and then Fe3O4 will be reduced to FeO and then FeO. So, these two reactions take place in the upper part of the blast furnace, because as the gas moves up, here reduction potential is high, as we will see the oxygen potential as it moves up, we will come to that thing. As the gas moves up, we will come into the thermodynamics later on. As the gas moves up, obviously the CO become converted to the CO2. So, its oxygen potential as it moves up is basically increases, or reduction potential decreases. But in this region, because the reduction potential requirement for Fe2O3, Fe3O4 is very low, so it can be easily take place. So, this reaction take place here. Even Fe3O4 to FeO also, reduction potential required is not that much, it also reduce significantly. So, these are the reaction, and then the carbon deposition reaction I will talk like this. This is the reverse reaction, twice CO break to CO2 and C. And then reaction in the middle zone, basically the indirect reduction. Basically in this isothermal zone, this reaction take place, FeO plus CO forming the Fe plus CO2, and this reaction also attains an equilibrium in this region, okay. So, this reaction become in equilibrium So this reaction attains equilibrium in the upper part of the isothermal zone, and here with this reaction take place throughout this section, middle section, this is middle section, in this section this reaction take place here and it attains equilibrium here. And also water gas shift reaction another in the middle region, that is the H2O plus CO forming H2CO2, this reaction also take place. And then reaction in the lower zone basically the direct reduction of FeO that take place. Direct reduction means FeO plus C, when the carbon directly participate in the reaction, it is called the direct reduction. Okay, these are called indirect reduction because here the carbon does not take place, the carbon does not participate into the reaction directly. It is the CO which is generated in the lower part of the furnace, and when it is moves up, then it reacts with this thing. Okay, so this type of reaction is called the indirect reduction, and this is also indirect reduction. This is the what about the CO that is generated here, this CO participate in this reaction, so it is also indirect reduction. But this reaction you can find that the carbon is directly participating in the reaction. Basically this reaction can be considered as a combination of the two reaction. This reaction if you can consider, then you can write it, that is the FeO plus CO forming Fe plus CO2, and then CO2 plus C forming twice CO. So this CO comes here and this CO2 goes here, right? And then if you combine this, then you will get FeO plus C is equal to Fe plus CO2. So this reaction basically this is the two reaction. This two reaction if you combine, then you can get this reaction. So directly participating means basically when the carbon directly participate into the reaction, that is called the direct reduction. Okay. So and this reaction basically you are basically generating the CO in situ, right? And this is a very endothermic reaction, highly endothermic reaction, and that's why this requires a higher temperature. So it takes place at higher temperature in the lower part of the furnace. All direct reductions are to take place in the lower part of the furnace, and some other reaction that can take place. Other direct reduction means P2O5, phosphorus pentoxide reacting with the carbon forming phosphorus and CO, and then silicon oxide reacting with the carbon forming silicon, manganese plus carbon forming Mn plus CO. So on this reaction is called the direct reduction because carbon directly participate and they form there. So this type of direct reduction highly endothermic and they take place in the lower part of the furnace. And then you have the sulfur reaction, that is the CaO plus sulfur plus carbon forming Cas plus CO. So sulfur basically get reduced, you can find from 0 state it goes to -2 state, so it get reduced in this way. So basically CaO plus sulfur plus CO, so this is also a sulfur reaction that take place in the, that is also in the lower part, we will discuss later on in detail. Okay. And then the raceway combustion reaction that I already have discussed, these are the two reaction, and if you combine it, it forms this thing. So this is the combustion reaction. So these are all the reactions. So in the upper part basically higher oxide get reduced, okay, because where the reduction potential required is less, as we will see the thermodynamics later on. And we have seen in the Ellingham diagram Fe2O3 is the top in position, then Fe3O4 and then FeO. So these two oxide get reduced in the upper part, whatever the reduction potential of the gas is sufficient to reduce them, and then this carbon deposition reaction, reverse of the carbon gasification reaction, this reverse reaction take place here at lower temperature. So carbon deposition can take place, and the middle region in the isothermal zone mostly there is the indirect reduction of FeO take place, and this indirect reduction come to an equilibrium in this region, that is called the chemical reserve zone, will come later on. And then this is your the water gas shift reaction also take place, and then in the lower part all the direct reduction take place, and all direct reduction are highly enthalpy consuming process, that is the highly endothermic. All direct reduction take place in the lower part of the furnace, right? And in the combustion region, as I said, first there is a C plus O2 CO2 and the CO2 in presence of carbon forming the CO gas, because CO is the most stable in the higher temperature. So finally these two reaction if you combine, you can get this thing. So these are the just at a glance what are the reactions that take place into the blast furnace. Of course, all these reaction details will come later on. So, what is this in this lecture? What we have discussed is that the blast furnace is tapered out in shaft and tapered in bottom to accommodate the material expansion and contraction, and there exists a long isothermal zone in the middle of the longitudinal section, and a chemical reserve zone exists in the upper part of the isothermal zone. As I said, upper part of the isothermal zone, Fu plus Cu is equal to Fe plus Cu2, that comes to an equilibrium, and that is called the chemical reactive zone. All the endothermic reaction take place in the lower part of the furnace. Indirect reduction of Oxide take place in the whole isothermal zone, while this reaction attains equilibrium in the chemical reserve zone, like this. And very important, an inverted V-shaped cohesive zone appears from the wash. Coke layers provides only the gas passage, and inactive coke zone, that is called the dead man coke, and it can be sitting or floating over the hearth. Okay, and this is the inactive coke, the dead man cokes, and this only takes the overburden of blast furnace, and raceway exists just at the tuer where basically your combustion of the gas take place. Okay, this is all. We will come to the next lecture. Thank you.